So switching topics and moving ever away from the surface of the Earth, starting with my talk, I'm going to be talking about the formation and properties of planetary moons. Our solar system, of course, is host to a large and diverse population of planetary satellites. Around the inner planets, the inner solid rocky planets, the most well-known satellite is, of course, our moon, but Mars also has two very tiny satellites, Phobos and Deimos. Around the gas giant planets, we find systems of satellites. These include some very spectacular individual objects, including icy Europa with its subsurface ocean at Jupiter, and Enceladus at Saturn, which we now know to be a geologically active object that is venting water-rich vapor plumes through geyser-like structures near its south pole. Moving up beyond Neptune, there's a population of so-called dwarf planets, including Pluto, but there are other large objects as well, and some of these are now known to also possess satellites. So we'd like to understand the distribution of these objects and how they formed, because, for one, they provide constraints on how our planets themselves formed. But also more broadly, we'd like to understand what this distribution of objects may tell us about the potential for moons in other planetary systems. So in recent years, the Kepler Space Telescope has identified thousands of exoplanets orbiting other stars by detecting the small decrease in the light from the star as the planet passes in front of the star, a transit event. The Kepler exoplanets are shown as the yellow circles on this plot that shows the radius of the planet in Earth radii as a function of its orbital period about its host star. The Kepler mission was designed to identify Earth-like planets, those with solid surfaces that could hold on to an Earth-like atmosphere for billions of years. And it's found many planets comparable in size to the Earth, but perhaps more surprisingly, it's identified a population of gas giant planets on very Earth-like orbits, planets that are probably similar in structure to the gas giants in our solar system. And in these systems, if we're interested in an Earth-like planet, the place where you would look would potentially be as a moon of one of these large gas giant planets on an Earth-like orbit. So I'm going to start with a very simple plot that shows properties of the satellite systems in our solar system. In blue are the satellite systems around the solid planets and dwarf planets. In orange, the satellite systems around the gas giants. So what I'm showing here is the mass of the whole satellite system ratioed to the mass of the planet as a function of the absolute mass of the planet in Earth masses. So around the solid planets, we see a very wide diversity in the relative size of moons compared to their host planets. The Pluto-Charon system is one extreme, with Charon containing more than 10% the mass of Pluto. And the two small satellites of Mars contain such a small fraction of Mars's mass, they don't even fall on this plot. In contrast to that diversity in relative masses, around the gas giants, we see nearly a constant satellite system mass ratio of order 10 to the minus 4. And so we'd like to understand at a basic level what could have given rise to these two different types of populations. So we think there are at least two processes, there are more also, that are effective producers of satellites. One most relevant for solid planets, the other for gas giants. Starting on the right, during the first few million years of its life, the sun was surrounded by a gas-rich disk, primarily hydrogen and helium gas by mass. And the gas giants were able to capture some of that mass because they grew to sizes large enough before that disk dissipated, to sizes of order 5 to 10 Earth masses, and at those masses they were able to gravitationally hold on to some of that hydrogen and helium gas. As the gas inflows to the planet, it tends to form a disk around the planet, which is a natural site for satellite formation. Now, the terrestrial planets and the dwarf planets never grew that large. Instead, we think the final stages of their formation were dominated by large impacts between other solid planet-sized objects. And so I'm going to start by talking about this mechanism of satellite formation. And the most work on this particular mechanism has been done in the context of our moon, which, as Frank mentioned, is one of the oldest questions in planetary science. So the moon contains about 1% of Earth's mass. It orbits at a distance right now of about 60 Earth radii from the Earth's center. But it hasn't been there. Its orbit has evolved substantially over its history. Tides raised by the moon on the Earth, and the interaction between the moon and those tides leads to a transfer of angular momentum from the Earth's spin to the moon's orbit, so that the Earth slows down and the moon's orbit expands over time. That process conserves angular momentum so that we know when the moon first formed, it was very close to the Earth and the Earth was spinning quite rapidly, with only about a 5-hour day. So the idea that the moon was formed from a giant impact with the Earth was first proposed in the post-Apollo era. The idea was that a large off-center collision with Earth and another planet-sized object delivered the angular momentum necessary to give Earth that 5-hour rotational day. And if debris from that collision was ejected into orbit around the Earth, the moon could then later accumulate from such a disk. So in order to try to model these types of collisions, there have been decades of work devoted toward developing ever-increasingly sophisticated three-dimensional hydrodynamical simulations of collisions. The commonly used method that I show here divides the impacting planet on the upper right and the target into typically hundreds of thousands to millions of individual particles, and the individual evolution of each particle is then tracked in time as it gravitationally interacts with all the other particles and responds to compressional heating, including phase changes during the impact event. So there's currently active debate about the exact nature of the moon-forming impact that can best explain the Earth-Moon features. This is one candidate that involves a Mars-sized impactor. So you'll see in this animation the impacting planet, shown in the upper right, will collide with the Earth. In the first few hours after the collision, the impacting object is destroyed. In this particular case, part of the impactor recoalesces gravitationally into an interior clump that will soon recollide with the Earth. There's the recollision. And an outer clump passes close to the Earth's surface and is disrupted. So after something like 24 hours of simulated time, you're left with an Earth rotating with about a 5-hour day, and it's surrounded by a disk that contains enough mass and angular momentum to later, we estimate a few hundred years later, accumulate into the moon. So this is an animation in 3D of the same impact simulation, and it'll give you a sense for the global scale of this event, the effect on the very figure of the Earth, and also the heating of the material by the impact. I call your attention to the color bar here. Red corresponds to fully vaporized rock at low pressures. There's the shock wave on the Earth generated by the impact. There's the re-impact coming of the inner clump. Our viewing point in this animation is slowly changing. So we're moving into the plane of the disk around the Earth. You can see the Earth is very oblate. It's rotating very quickly at this point. Now our viewing point's moving under the planet, looking up, and there's the outer clump as it passes close to the Earth and is disrupted. So we use these types of models to study in particular what can best give us the Earth-Moon system, but also more generally to learn how impacts can produce moons. So in this animation, I've mapped the final state of each of these particles as a color onto the end state of the simulation. So the yellow particles are those that end up in the disk, that could form the satellite later on. The blue particles are those that end up in the planet, and the red particles are those that, escape. So preserving this mapping and running the simulation backwards, one finds that in these types of collisions, it's often the case that most of the material that ends up in the disk originates from a single region of the impacting planet, the yellow particles here. And it's this region that's most effectively torqued into bound orbit through gravitational interactions with the distorted figure of the Earth and the impactor in the hours right after the initial impact. Now, because for many of these collisions, the material that produces the satellite comes from a single region of the impactor that grazes past the target, one finds that as you increase the relative size of the impactor compared to the planet, you produce relatively more massive disk. Conversely, if you decrease the relative size of the impactor compared to the planet, you put less material into orbit. For low velocities, the same is true as you make the impact more grazing. As it becomes more oblique, you tend to make more massive disk. So what this implies is if you imagine a natural variation in the types of collisions that would have happened in the final stages of planet formation, you would have produced satellite systems with very different mass ratios. So on the left is an extreme case of an impactor that's almost as large as the target itself. This particular case is an impact that can produce a Pluto-Charon type system with a very large mass ratio between the satellite and the planet. Conversely, on the right is a much smaller impactor. It's still a giant impactor, and it produces a disk, but ultimately a much smaller satellite relative to the planet. So we think these physical collisions, when it comes to forming satellites of solid planets, offer a good explanation for the diversity of systems that we see in our solar system. So let me now turn to the satellite systems around the gas giants, and I'm going to focus on Jupiter and Saturn in particular. So Jupiter, of course, we have the 4 very famous Galilean satellites. They're on nearly circular coplanar orbits. If you take their mass, you sum all their masses, you ratio it to the mass of Jupiter, you get a mass ratio of 2 times 10 to the negative 4. At Saturn, we have a system that looks very different. Big ring system, lots of small and intermediate moons, only one large satellite, in this case, Titan. And yet still, if you sum up the mass in all of these satellites and ratio it to the mass of Saturn, you get nearly the same mass ratio, 2.5 times 10 to the minus 4. So I mentioned earlier that the gas planets acquired their gas as gas inflowed to the planets from the circumsolar nebular disk. Now, as this material flowed into the planet, it had too much specific angular momentum to fall directly to the planet. And so it would instead form a circumplanetary disk around the planet. So this disk would be composed primarily of hydrogen and helium gas, but would also include any small entrained rock and ice solids. So the picture is, viewed here on edge, that we had a gas-rich disk around these planets within which the rock and ice particles would orbit, mutually collide, and grow into satellites. Now, as satellites grow within a primarily gaseous disk, there's an important mode of interaction between the satellites and the disk that takes place. So this is an animation showing the gas density of a disk. We're looking down from above as it's perturbed by a roughly Galilean-sized moon. So the moon perturbs the disk, and these perturbations propagate as spiral density waves. The spiral wave pattern, which is then non-axisymmetric, exerts a torque on the satellite orbit. And this torque is actually negative, so it causes the satellite's orbit to spiral inward towards the planet. Now, the rate at which the satellite spirals inward is proportional to the mass of the satellite. The bigger the satellite, the faster its orbit will decay or migrate into the planet. And it's also proportional to the density of the gas disk. And this mode of interaction is well known, and it's known as type 1 migration. So I'm going to show you some results from a model that's trying to mimic this basic situation where you're forming satellites around a gas planet whose disk is being supplied by an inflow of gas and small solids. The model is tracking the orbits of the solid particles around the planet, and when they collide, it's assuming they merge to form larger satellites, and it's including this type 1 interaction between the gas disk and the satellites. So on the plot on the lower left, the black circles will be the simulated satellites. The horizontal line between each one is proportional to how elliptical its orbit is. As the satellites grow, due to the inflowing mass to the disk, they'll move up the plot and the circles will increase in size in proportion to the size of the satellites. Now on the x-axis is distance from the planet. So as this type 1 migration kicks in, which it does as satellites get large, you'll see the satellites move to the left until finally, when they would collide with a nominal planetary surface near the y-axis, they're removed from the simulation. And the plot on the left is going to show the evolution of the total satellite system mass in this same simulation as a function of time. So the inflow to the disk supplies material. A system of multiple satellites grows. It starts to undergo type 1 migration, and large satellites are one by one lost to collision with the planet. The inflow continues, and a new generation of satellites is formed, and then again lost. Looking on the plot on the right, you can see that this forming and losing of generations of satellites causes the total mass in the satellite system to oscillate about roughly a constant value of order 10 to the minus 4. It goes up as inflow is delivered to the disk, and it decreases in discrete jumps as large satellites collide with the planet's surface. So this model, which is quite simple, gives us a prediction that the total satellite system mass compared to the planet might be a constant value, roughly independent of the total amount of mass processed through this disk. Now, I mentioned that the sun only holds on to its gas-rich disk for a few million years. The disk then dissipates, the inflow of gas to the planet stops, and the gas disk around the planet dissipates as well. At this point, a final system of satellites can stabilize. So in these simulations, the inflow supply to the disk around the planet is time-dependent. We're concentrating on what the final generation of satellites might look like as a result of this simple combination of processes. In the upper case, you can see as the inflow ends to the disk, the total satellite system mass asymptotes, and we're left with a system of 4 large satellites that's broadly similar to the Galilean system, shown here in red. Now, in the bottom simulation, the same parameters are used, except the inflow is assumed to decay with a slightly different rate. So the timing of when the inflow stops relative to these cycles of satellite formation and loss is slightly different. And in this case, you end up with a final system that has one dominant large satellite, a crude analog to the Saturnian system. So these types of models suggest that the similarity in satellite system mass ratio that we see in our system may not be coincidence. There may actually be a physical reason behind it. There's a very new project ongoing that is seeking to find exomoons, moons of exoplanets within the Kepler dataset. This is extremely challenging. They are attempting to detect the signature of a small moon orbiting an exoplanet as this system passes in front of a distant star. Each planet that they analyze takes literally tens of thousands of CPU hours. To date, they have detected no exomoons. However, they've now analyzed many tens of planets, and they've come up with some interesting upper limits for those objects. So their upper limits are shown here as the black triangles. Each triangle corresponds to a different exoplanet and represents at the 95% confidence level that that planet does not have a moon at that point or larger. It could have a moon anywhere below that point, or it could not have a moon at all. So an interesting thing to note is that this technique in general is sensitive enough that if large mass ratio satellites were common around gas giants in other solar systems, say mass ratios like that of the Earth to the Moon or Pluto to Charon, they probably would have already detected an exomoon. And in general, this is suggestive that perhaps there may also be a limit on the satellite system mass ratio in other systems similar to what we see. We don't know that yet. We don't actually have any detections, and we don't know where these points will actually fall relative to the values for our solar system. But if we were to suppose that, at least in many systems, similar processes may be responsible for satellite production as in our own system, we can ask, where would be the most promising place to look if one was interested in an Earth-like exomoon? A moon large enough to hold on to an Earth-like atmosphere for billions of years? And the result is shown here in this plot. The most promising region of parameter space to find these large moons would be around very large exoplanets, planets that have several times the mass of Jupiter. Another potential region of parameter space would be around planets several times the mass of the Earth, which, if they had, say, a Charon to Pluto type mass ratio, might have produced a Mars-size or larger satellite through a giant impact. In the next several years, they are going to be able to extend this data set to several hundred additional planets. Hopefully there will be a suite of actual detections of exoplanets, and we'll be able to learn about their distribution. In particular, we're interested in a size range we know little about based on our solar system, and that is objects that fall in between the mass of the Earth and the mass of Uranus and Neptune. We don't have any objects in that size range in our solar system, and yet in the Kepler data set, there are many such objects. And so it seems clear that if we do detect exomoons, we're going to learn something fundamental about the formation of satellites and perhaps planets and their properties in this size range. Thank you.